So today the next homologous series we will look at under hydrocarbons is the homologous series of alkenes. Alkenes are just, they are not like alkanes. Remember when we talk about alkanes, what make alkanes is the carbon to carbon single bond. And we said alkanes are saturated hydrocarbons. Today we look at the alkenes. Alkenes is one of the unsaturated hydrocarbons. It contains at least one carbon to carbon double bond. Remember, this is for our alkanes. When we have carbon to carbon double bond in a compound, at least one of them, the compound can be an alkene, can belong, or the compound may belong to the alkene family. Now, so the what makes, remember when we said carbon to carbon single bond, we said that single bond is a sigma bond. But for carbon to carbon double bond, it means we have one sigma bond and one pi bond. So the presence So the presence of the pi bond in the double bond makes them much more reactive than alkanes. So alkenes are more reactive than alkanes because of the double bond. So they are also known as olefin. Remember, alkanes are known as, they're also known as paraffin, but we know alkenes also as olefin. So when we say olefin, it's from oleum, which means oil forming. So because many alkenes, they formed oily products when reacted with halogens. So that is why they call them olefin. Now, what is the general molecular formula for alkenes? Remember, for alkane is CnH2n plus 2. Now, for the alkene, it is CnH2n. That is the general molecular formula for alkene. So from that, we can name any member. We can draw the structure of any member of alkene from this general molecular formula. Let's look at the simplest member. The simplest member is going to be when n equals 1. Is that possible? Let's see. Remember, for this, for alkane, when n equals 1, it means it's going to be C1 H2 times 1 plus 1. So this is for the alkene, which means it is CH4. This is the, plus 2, CH4. Now for alkene, can we have it that way? N equals 1 for alkene. Is that possible? If you try that, we are going to get C1 H2 times 1, which means we have CH2. There is no CH2. So, no CH2 because the smallest member of alkene family has to contain 2 carbon atoms because what the signature of alkene is carbon to carbon double bond. So when we have only 1 carbon atom, there's no presence of double bond. So the smallest member of alkene family will have n equals 2. So when n equals 2, we are going to have C2H2 times 2, which is going to be C2H4. And this is what? This is ethene. So ethene is the smallest family member of the alkene. Something like this, CH, H, H, and H. So this is C2H4. So we talked about nomenclature already, so you can just go over the naming of alkene family members. So from here, we will move on to the structure of the alkenes. So we look at the structure of the alkene. Remember, the structure of alkene is tetrahedra. So tetrahedra is the structure of alkene, and then the bond angle is 109.5, if you remember. For the alkene, the structure is planar geometry. So that is the structure. We have tetrahedral geometry. For this one, it is planar geometry. So uh, when we say planar geometry, it means we are talking about there are two carbon atoms that are involved. That is, these two carbon atoms like this. They are involved in the double bond, and the atoms directly attached to them, they lie in a single plane. So that is why we say they are planar. What about the hybridization? Remember, hybridization for alkane is what? sp3. So that is for the alkene. Now for the alkene, what is the hybridization there? So the hybridization for alkene is what? sp2. We discussed this in the past before. So I will not go deep into hybridization. We just know that it forms trigonal planar geometry. So that is why we have planar. That's why the shape is planar geometry, because it involves one s orbital and 2p orbital. So, but in the case of tetrahedra over there, it involves one s orbital and 3p orbitals. Now, remember, we said it contains one pi bond, and then the double bond means a pi bond and then a sigma bond. So, uh, the pi bond is weaker than the sigma bond. So the sigma bond is strong, and then the pi bond is weak. So the pi bond is formed by the sideway overlap of pi orbital. We mentioned all this actually when we were discussing geometry, or when we're discussing hybridization. So you can go over that again if you want to know more about the hybridization in alkene. Now we'll go to synthesis of the alkenes. How do we produce alkene in the lab? So number one way of making the alkenes in the lab is by dehydration. Dehydration of alcohols. That is, removing of water molecule from an alcohol using an acid catalyst. It is very important you mention the catalyst used for the reaction. So let's look at a general equation for that. Are we right? Instead of let's look at this. Sorry, this may not be clear enough. So we have this an alkyl, remember? And then we have our CH2, a double bond, double bond, CH2, CH2OH. So this is an alcohol. So this is an alcohol, our reactant. So alcohol will undergo dehydration. So what do we use to dehydrate alcohol? The catalyst that is used is concentrated sulfuric acid, conc H2SO4, and then the reaction also happen at elevated temperature. So we need to heat the reaction. And then what are we going to have? We will have, just look at it, this R will still be there, the alkyl, and then we have C, instead of CH2, it becomes CH, and then the single bond becomes double bond. There's reason behind that when we go to a reaction mechanism, but we don't need to discuss that right now. So we have CH2 now. OH is gone. So OH is gone. Remember, if OH is gone, and then one H here, this OH is gone, and then one of the two hydrogen here is gone. So it means we are going to get HOH. What is HOH? HOH is water. So we have removed water molecule from alcohol to get an alkene, and then water as our product. So let us look at a typical example of this. We are going to use ethanol as an example, CH3, CH2OH. If you like, you can draw the structure. So let's draw the structure. Just a display formula so we can get it better. I have COH and then our hydrogen atom. And then this one undergoes dehydration in the presence of conc H2SO4 and heat. Don't forget to mention the condition of the reaction. It is very important. So this OH will go, and this one of the hydrogen atoms here will go. Remember, it is important you don't remove the OH and then H, both of them at one carbon atom here. You don't do that because you are forming double bond, and double bond is across the two carbon atoms. So one will give the OH, the other carbon atom will give the H. So our product is going to be carbon that has only two hydrogen atoms left, the bond, the other carbon that has only two hydrogen atoms left. When it's like this, it means it's supposed to be double bond here. Of course, the bond breaks here, and then this bond also break. So one of the electron here is used with the electron here to give us a single bond here, to give us another bond here. So one of the bond is sigma bond, and the other one is pi bond. So when H and OH goes, they give us H2O as the product. So that is the dehydration of alcohol to give us dehydration of ethanol to give us ethane. So this is ethanol and this is ethene as the product.